Welcome back. So week 8, we're primarily looking into, oops, that shouldn't be there, but we're primarily looking into relative motion. The first problem is based on relative velocity. We technically do cover 5.5 in the course, but it's a very situational method, and even though it works with velocity, it breaks apart when you look at acceleration. Usually the chapter 5 problem, they'll ask you velocity in part A, acceleration in part B, and if you have to switch method halfway through a problem, that's going to cause issues. So I personally advise strongly against, relying on instantaneous center of zero velocity or ICZV. Anything you can do with IC approach, relative motion does it better. So lastly, we have the relative velocity, basically VB is equal to VA plus VB relative to A. The idea is that you basically just update it for acceleration. The relative acceleration is basically written out the same way. AB is equal to AA plus AB relative to A. Now, that's just for the relative acceleration, but when you actually write it out in terms of the whole form, like a cross product or IG coordinate, things gets a little bit more complicated. So similar to how we did it with relative velocity, when you have translation plus rotation, you can break it down. And same thing with acceleration. So let's say it is spinning, it has an omega, it has an alpha. You can just break the acceleration down into translation plus the rotation aspect of it. Now, the actual derivation is kind of based on trigonometry. The idea is that you're going to have, actually not this one, sorry. So it's a relative velocity, acceleration has a normal and tangential. Because when you break it down to the rotation, every translation part is just basically thrown into the first section. So you can just basically think of it as like if you're following point A, point B is just doing a fixed rotation, and then you don't even have to use r theta or anything like that, just slap nt coordinates on top. As usual, this is 90 degrees, it points at the tangential direction, and then the magnitude is usually somewhere basically a combination of the tangential and the normal acceleration. This is basically what you need. Negative omega square RB relative to A, and also alpha cross RB relative to A. Now, here between omega square and R, there's no cross product, and the equation is already derived to be ready to be used. The alpha cross RB relative to A, that does have a cross product. Do not add a cross product into after omega squared, it will break apart. The reason is that, and you can actually do it yourself, prove it yourself, there's a cross product that's already been built in, so you don't have to do extra work for it. So this is basically the most convenient form of the equation. And then this whole thing is basically representing your relative acceleration. Sometimes it's written out like this format. I personally don't like it. Eventually it's going to give you the third line, which is your relative acceleration for rigid body motion. If there's no normal acceleration or no tangential acceleration, that term's just going to get crossed out as 0 anyway. Depending on which script sheet you're using, if you're using the one from the Kirkus, at least in the tutorial page, there is a typo here, or sorry, that one is correct, but there's a typo here that alpha is missing the cross product after it. Again, omega square RB relative to A, no cross product. Alpha RB relative to A, yes, cross product. So remember to put that in if you're using the vector approach. Questions? Again, similar to velocity or relative velocity, you primarily want to work with basically the joints and the pins of a system. Sometimes it'll be funny to ask you, like, say, what's the acceleration gravitational center? In that case, you still prefer working the pins and then finally work your way through because usually if it's like the same rod, then it's going to have the same omega and the same alpha. And if it's like things like, fixed pin, this is point A, this is point B, then again, the pin is not going anywhere, so that'll also simplify the problem a little bit. Similar, even more so than like say, relative velocity, your kinematic diagram is very important. You don't want to just draw an FBD. You want to repeat the same thing again, but with a kinematic diagram where you draw things like velocity, omega, alpha, and acceleration. Don't try to cramp it all in the same figure. It gets messy. Questions so far? Okay. So there's some cases where the problem can get simplified. Usually they wouldn't tell you, but you have to look at the problem to come up with the conclusion. Quite often when you have no slipping, or in this case, let's say gears, you got the teeth that's rotating. At the contact point, the velocity and the acceleration is going to be the same. Because if there's difference in velocity, then you're basically breaking the teeth off, right? You're breaking the system, and we don't break system in this course. So when that happens, the tangential acceleration, same with the tangential velocity, are the same. And then you can replace it with R alpha. So alpha R on one side equals alpha R on the other side. Usually this sometimes could be like a hidden assumption that the question wants you to come up with. Now, however, that does not mean your normal acceleration is the same, because if you look at it, the normal acceleration is v squared divided by r. If the radius changes, then your normal acceleration is not going to be the same. Unless you have two symmetrical things, and then there's no slipping, then you have the same, basically everything, but then they wouldn't ask you something that straightforward in exams. Questions? Okay. Rolling slipping. Oh, without slipping first. With slipping gets very tricky. So in the middle, this is kind of like the one use of like the IC approach that I think is somewhat useful. Without slipping, at the contact point of the floor, the velocity equals 0, right? Because if there is a non-zero, then there's slipping. When that happens, if you have the omega of the body, you can find the velocity at, say, the gravitational center, or even like a random point called C. You just need to basically find the relative displacement. Now, the usefulness of IC approach kind of stops here, because if you look at the right, if you think about the acceleration, so right before it touches the floor, it's going to have a kind of downward velocity, right? Because it's kind of rolling down. After the floor is kind of basically rotating up, so there's an upward velocity. That means there's an acceleration. And if there's an acceleration, that means, A isn't equal to 0, so there's no such thing as 0 acceleration, or, IC of 0, or, IC of 0A. Doesn't work, and you have to basically go back to using relative motion. Again, it's not ideal to switch halfway from like IC to acceleration or like a relative motion approach. Question? Yep. No, so anything IC can do, relative motion can also do. Hot take, personal hot take, relative motion does it better. I graded like 600 papers last year on chapter 5. So with vector or matrix approach, there's more meat for me to see what happened if something went wrong. With a IC approach, it's just a triangle, and you can see a lot of weird triangle shape where I'm just like, I have no idea what you did. It's very hard to like basically give points because of that. Yep. Good. So we don't have rolling problems today, but you might have to use it for your assignment 7. So these are just kind of extra slides. Move on to question 1. Set upside down. It's not rotating. It's not rotating. Yeah, it's kind of stuck. There we go. Sorry about that. My screen decided not to rotate with the HDMI cable plugged in. So you guys have technically did similar problems like this over the weekend for your assignment 6. But as you look into assignment 7, basically F equals ma, your acceleration is still going to be on the right-hand side of the equation. The only tricky part is basically the left side where you break it down to ij coordinates. So the first problem is velocity-based. But to get acceleration, quite often you also need to find velocity first. So we have a crank mechanism. We're given an omega is clockwise, 0.8 radian per second. It's moving a bunch of stuff. So I have converted the unit into metric, so you can just scratch those out and replace it with the metric version. The question is asking us to find VA and VZ. We are given omega OB of 0.8 radian per second. However, counterclockwise positive, the omega is given to us as clockwise, so this is actually a negative 0.8 radian per second in a k direction. So that's another location where the problem can slip you up by simply flipping the sign. Remember the 3 steps guide for solving these problems. It still applies for relative acceleration and even for, like, say, chapter 6 when you mix this with Newton's second law. So we start with pin O. That's fixed. It only rotates, and it connects to B. And it comes down to here, to point A. Conveniently, point A is directly below O. And this is at a 20 degrees. Oh, wait, no, that's not 20 degrees. We're given omega OB. That gives us VB, basically perpendicular. Again, that's because pin O is basically fixed, so it can only rotate. So this is just a fixed center rotation problem, not even relative motion yet. We also have point C, but we don't really care about it yet. We just want to find omega AB and VA, then that allows us to find point C. Now, if you think about the system, as OB kind of rotates or rotates downward clockwise, it's going to push A down, right? So it's going to basically go that way, velocity A. However, let's say I kind of, I panic or like I didn't really think about it. I'm just going to assume it goes upward, right? I'm going to assume VA goes upward, and that's how my solution went, and it's going to give you the correct answer. This is the beauty with the vector approach. As long as you're consistent, you're going to be all right. So VA at 20 degrees. We know this is 10 inches, which is 0.254 meter. We know this is 0.508 meter. and that gives us an h of squared minus 0.254 squared of 0.44 meter. Again, do not be afraid to draw more triangle. Yep, go ahead. Yes, that's how it should be, but basically, I'm going to prove that even if you predict the wrong direction, it will still work out. Exactly, it's just going to show me a negative value. Everything is going to actually check out. We got H. Questions so far? Okay, so some of the other things we want is RB relative to O. B is on the right, so imagine this is your origin. You're just going to have basically a plus 0.254i and 0j. Now, with RB relative to A, you can imagine we're moving the origin to where A is. B is still positive in terms of both x and y relative coordinates, so it's still going to be just plus. So 0.254i plus 0.44j, which is basically just the h we've calculated just now. We also want to break our VA down into x. Yep. That's an R, sorry. This is a relative displacement. Yeah, we unfortunately don't have forces this week yet. Yeah. Okay, so next thing we're going to break our VA down into basically VAXI plus VAYJ. You can also do this later, but I tend to like getting this done out of the way earlier. Now, if you assume that's going in the opposite direction, then you have a negative value associated to it instead of in positive I and j. But in this case, like I said, the solution will just get a negative answer. Questions so far? Okay, let's go on to step 2. So usually it's a good idea to just write down which pin or which point you're going from. In this case, we're going from point O to point B first. We're basically analyzing this linkage. Then I'm going like O to B. So with a vector method, you're going to have VB is equal to V naught plus omega OB cross RB relative to O. You might have spotted here I wrote omega OB instead of omega BO. They are the same. Because again, they're the same body, right? So they're going to have the same omega. What is important is that you make sure these, the relative displacement, are actually consistent. Because that one, if you flip it, then it actually changes the answer. Point O is a pin, so zero velocity. We are given omega OB earlier. So negative 0.8 K cross 0.254 I. K cross I gives us positive J. There is a negative sign here, so that has to be conserved. Given us negative 0.203 J meter per second. You can also use a scalar approach, and since like OB is just circular motion, V is equal to R omega, and it's going to give you the same, but you have to give it a sign, the negative sign, manually afterwards. Questions? Okay, we found B. That's the easier one. Now let's look at A. You can do B to A, but I usually like kind of like converging onto a point when you get like multiple rods. It doesn't change the solution. Oh, sorry, it changes the steps, but the answer is going to be the same nonetheless. So we're going from A to B. VB is on the right, and then VA, left, and then VA plus omega AB cross RB relative to A on the right side. We already found VB, so I can plug that right in. We don't know VA yet, but we did have an expression for it. We don't know omega AB. But we have already found the relative displacement. K cross I gives you positive J. K cross J gives you negative I. So left-hand side is the same. These are still the same, but you're going to get plus 0.254 omega A B J minus 0.44 omega A B I. Questions so far? The next step, step 3, is basically when we break everything into I and J. As you move on, like especially in chapter 6, you're going to have a pretty lengthy equation. So what I usually like is that put a little annotation. Let's say this one is like in the y direction, this one is the x, this one is y, this one is in the y, this one is in the x. So just to give myself like a clear reference, basically what is in the x or y direction, because it's pretty easy to mix up I and j depending on how fast your handwriting is or how clear it is. And a good thing is once you actually construct the I and j equation, you can cross the terms out to make sure you haven't duplicate or miss any terms. So on the left, there's no I, so 0 gives us VA sine 20 degrees. Oh, sorry. This is basically just VAX. It's not VAX cosine 20 or VAY sine 20. Sorry about that. VA sine 20 plus 0.254 omega AB. So we got two terms. Again, cross them out as you're done with it, just to make sure you haven't missed anything. We can rearrange this into omega AB equals VA. Oh, yep, that's right. That's actually cosine 20 degrees. Cosine 20 degrees plus, wait. Oh, whoops, my bad, copy the wrong equation. Well, I've lost 5 marks in an exam. Okay, like this, like say the velocity would be basically 10 points, so you get 5 questions normally. If it's out of 100, each question has like 20 points. Split into 2 or 3 parts, 10 points each, and then this It depends on the grader. Last year, this would be maybe not 5 marks, maybe like 2 or 3. But it really does depend on the grader. So B8 cosine 20 divided by 0.44. It's the only problem with relative or like rigid body problems. The amount of writing and copying actually does kind of lead to more chances of like typographical error. But having the vector approach is easy to catch this, hopefully, when you basically do a second run. Questions on omega AB so far? Then for the J direction, we have negative 0.203 on the left, V8 sine 20 degrees on the right, plus 0.25 for omega AB. We've got 3 terms, cancels out. And you can sub our omega AB expression into our new J equation. Left-hand side stays the same. And that's going to give you VA is negative 0.23 meter per second. Now remember how we assume that VA is going in basically the wrong direction. We get a negative value. Technically, you're still supposed to break it into I and J component, but even if you do, it's just going to tell you that both of them are in the negative direction, and the wheel VA is in the negative direction. If you plug this back into our omega AB equation, that's going to give us omega AB of negative 0.49 radian per second. Questions on VA, omega AB? Yep. Right, so we're assuming that it was in the positive rotation. With the vector approach, yeah. It's the same as like a VA. Usually what I would do is assume it's always in a positive direction. And then in this case, it gives us negative, which means it's going to be in clockwise. So if you think about the system, it does make sense that, you know, if VA is actually going downward, your BC is also kind of going to rotate clockwise, similar to your OB, and negative kind of checks out. Yeah, if it's like positive, then A would actually move upward instead. Correct, yep. The question also asks for basically VC and omega C. The good thing with finding VA is that allows us to also find VC. We're basically just repeating step 2, brought from A to C. RC relative to A. So if we just quickly sketch this out again, this is 0, B, A. C is kind of like at the midpoint. And you can actually, break this into like a, you don't even need like a similar triangle. It's just a midpoint, so you can just do like x divided by 2, and also the height divided by 2 to get the relative displacement. Questions? You throw that in, eventually it's just going to give you Vc, which is equal to negative 0.108i minus 0.141j. Skipped quite a bit of 2-3 lines here, but it's just the same, pretty similar to what we did, but with different vectors. Finally, we can also report the magnitude. Questions? Yep. Yep, sorry, I probably should have mentioned it. So they are basically on the same body, right? So basically at any point, the omega is going to be the same. The velocity isn't, but it's like imagine here, right? This is your rod. No matter how rotated, the omega and alpha of the body at every point is going to be the same. Like unless you have like a pin, then that's going to change it up. But in the same rod, the omega alpha has to hold. Yep. No, I don't think. Can actually try it. V is 0.23. VB is like in an I and J. No, it wouldn't. I. Yeah, so 0.1015, but we got 0.108. You can try the Y direction to see if it also. Oh. Interesting. I'm tempted to say it just got lucky in this case. Yeah, I have to look at more example if that holds. But if it does, then that's a very, very convenient method. But assume it doesn't hold, you can also ask your prof. I wouldn't assume it. Yeah, try around, like especially a different system. Questions before we move on to problem 2? Yep. Find what? Alpha A, B. Yeah, so the second problem goes into basically alpha and acceleration. But basically, alpha A, B. Oh, you need the acceleration for basically some of the system. Because then right now, we have basically, does it tell us clockwise? Yeah, it hasn't told us any velocity. If you look at the acceleration equation, yeah, we have omega, but we don't have AB, we don't have AA. Yeah, so in that case, we need more info. And like, they will probably give it to you in a question, like in a problem in exam. Questions? Okay. So we're going to move on to problem 2, which is actually a relative acceleration problem. So the mechanism itself looks pretty complicated. Quite often they like to mess around by giving you these kind of weird shape, a triangle, or you can get a star shape if they want. The shape itself doesn't matter. What does matter is basically the radius, right? So let's redraw the system first. We have D. Point B is directly downward. And then A is around here. And then we have O somewhere up there. Actually, it should be the same altitude. We have this kind of pizza shape disk. And then we have a point E here. The question tried to be a bit mischievous by having all these stuff around here that makes it look more complicated by looping around the pulley. But the string itself, it says flexible, but if flexible means that it can bend, in this case, it doesn't mean it can elongate, because if it can stretch, that breaks the entire problem. So it's not stretchable or non-deformable, it just means it can loop around. And in this case, VE is actually just the same as our V, or 2 meters per second. Basically the speed of the rope that's being pulled, because it's directly connected to that point. We're going to assume a omega BD of counterclockwise. This because basically VE is going towards the right, so the whole system is just going to rotate towards the right. Now because BD and AO are both vertical, they're going to have the same direction of velocity, basically just perpendicular to the origin of its own axis. And that's going to give us omega AO. Questions? Again, the pizza shape looks pretty weird, but at least for AO, it's just the same as like having a straight rod. Yep. The tangential acceleration at E is 0 if the speed is constant. Yeah, because omega. Okay. You have a question? Yep. Yep. So you can almost basically think of this system as a rod, like because it's basically pinned at O, right? So no matter where it goes, it can just go like rotation, fixed axis rotation, and that means it has to be 90 degrees, like tangential. First step is to find VA. Omega AO is equal to omega EO because they're on the same body. V is equal to R omega. We can rearrange it into omega equals V divided by R. That's going to give us VA divided by RAO equals VE divided by REO. giving us VA equals 1.5 meter per second. This is a scalar approach, but I don't think it's necessary to do a vector approach. It's just going to give you positive 1.5 meter per second I. In this case, we can manually assign it. Now we also want to find VB, but in that case we're going to go from D to B. The reason is that we know the velocity of point D is 0. Now, it might seem like we're kind of stuck here because, well, we don't know omega AB, but actually we do. And at this instant, omega AB is equal to 0. And that's because they are parallel. Right? If they're both parallel, and that only holds for this second or this moment that we're analyzing it, then there is no omega. And it's, again, this is only because the system is very nicely laid out, where O or dB and also, dB and OA are both vertical parallel, and then the velocities are also parallel. If they kind of switch some of them around, even 1 degree, then this assumption breaks apart. Then we have to actually ask them for it, or we have to need more info to calculate it. If that's 0, that just gives us a fancy way of writing VB is equal to VA. Nope. VB equals VA. Questions? Yep. No, so because AB is at 2 different points of the rod, right? They're 2 different pins, and like with other relative motion problem, if there is a general motion, rotation, then they're not going to be the same. At this instant, it's going through pure curved linear translation, but it's only at this instant, I think. Yeah, because then we're trying to find alpha AB. That means it is going to have omega AB, just not at this second. Yep. Correct. They have to be on the same body. So AB is basically 2 ends of the same body. Yep. So we know it's pure translation because it's actually from, so we had to draw the VA and VB vector first, right? Because it's very hard to tell if it's pure translation, especially with the radius is different. But in this case, because they're both kind of the direction vector. So this is what we have, right? So the velocities are basically perpendicular. Now let's say we tweak this to this. So this is our new B. The velocity is going that way. Our velocity is going that way. Then the rod is eventually going to actually have to rotate. There's going to be an omega. Make sense? Okay, VA. Okay, next up, is from D to B. Wait, have we find? Oh, we did. Oh, actually, that's when we finally applied the acceleration. So AB is equal to AD minus omega BD squared, RB relative to D. Again, no cross product. plus alpha BD cross RB relative to D. Yes, cross product. Point D is the pin. We know it's not going anywhere. 0. That's going to give us AB equals omega BD. We just found phi B, so we can actually find omega BD. So V is equal to R omega. That's going to give us omega BD of 8.33 radian per second. This is like scalar approach. If you want to be accurate, you can write it out in a vector approach, but if we don't have to use cross product, then why bother with it? So that's going to give us AB is equal to negative 8.33 squared, 0I minus 0.18J. Because again, B is basically vertically below point D, so there's not going to be any I. It is below D, so that's going to have the negative sign. Plus alpha BDK cross 0I minus 0.18J. You might have noticed I didn't even write the K there. Again, because it's already been squared, this is where the negative actually, the negative comes from. So don't write a K, because then you're going to actually accidentally do a cross product where there shouldn't be. This one, however, does need it. 0, there's nothing. K cross J give us negative I. There's already a negative inside, so that turns into positive. So that gives us an AB of 12.49J plus 0.18 alpha BDI. Questions? Yep. So because BD is basically fixed axis rotation, so when you have fixed axis rotation, it's like the OG yo-yo problem, anti-coordinate, low orbit. It's just a pure circular motion. Cross product will give you the same answer. In fact, it will give you the direction, but in this case, it's positive. It's going to give us a positive rotation counterclockwise. Okay. The next step is basically linking from point B to point A. After all, we are trying to find alpha AB. So point B here and point A here. We do need basically the delta X and delta Y. The question gave us the angle, 15 degrees, and also length AB. So with that, we can basically find the horizontal displacement and the actual vertical displacement. So positive 0.34I, but A is actually at a lower altitude, so negative 0.12J. Questions on how we got RAB? Finally, we can write out the relative acceleration. AA is equal to AB. minus omega AB squared RA relative to B plus alpha AB cross R relative or A relative to B. Again, we established earlier omega AB is 0 because the velocities are parallel at that instant. That's going to simplify the equation a little bit. Again, our AB kind of comes in here. K cross I, positive J, K cross J, negative I, which cancels out, becomes a positive. This is just basically the same step, but with the actual cross product performed. Questions so far? So it seems like we're stuck again. We have one equation, but we have both alpha BD, alpha AB. And we also don't know AA, but the question actually gave us a hint. It mentioned that the band is being pulled at a constant speed. And as one of your classmates have pointed out, that means the tangential acceleration is 0 at that moment. Because constant VE. You might be saying, well, point A is here, point E is there. How does it translate? They're on the same body, right? So if the alpha, which is basically what the VE tells us is basically constant or 0 in this case, that tells us the tangential acceleration for point A is also 0. The normal acceleration is, however, not 0. But we have everything we need to calculate it, which is equal to 7.5 J. We know it's going to point directly upward because normal acceleration always points towards the center of the rotation. So it's just going to give us positive in the J direction in this case. Questions? Zero alpha BD. So then you can go from O to A. This is going to give you basically your alpha. Actually, we don't even need alpha AO. Sorry, actually, you don't even need this. You can just plug it directly into our acceleration. The I is going to basically give us 0 equals 0.1 0.8 alpha BD plus 0.12 alpha AB. This is X, this is X, Y, Y, Y. Rearranging give us alpha BD equals negative 0.67 alpha AB. Again, all we're doing is basically, we found out the tangential acceleration is 0, we found the normal acceleration, and then you just plug it back in, and then break it into the I and J direction. Yeah, you can go OA, which is basically what my note did when I was trying to solve it, and then I realized you don't need it. I guess that's why I kind of stopped there. With alpha BD, you plug in the J direction. It's going to give you an alpha AB of 14.7 radian per second squared. So it turns out you don't even need to solve alpha BD, but it might not always be obvious when you're writing this out. Negative, so the alpha is actually in a clockwise direction, which kind of makes sense. As you kind of spin that way, the rod is going to basically get kind of pushed down like that. Questions? So you don't have to converge at A. You can converge at point B with the cross product or the vector approach. It's just going to give you the same solution. Yeah, we'll have a 5 minutes water break, and then we'll jump back into question 3 for today. Yep.
How does it clip on?
So yeah, it's a pretty weird looking mechanism.
Like that?
Yeah.
Test, test. Can you see like the amplitude of my voice? Testing?
Yep. Yeah. I'll say just get it put down. Maybe on this side.
Yeah, right. Okay, testing, testing.
Yeah.
Okay. All right, guys, so we'll do the last problem for today. Guys, this last problem for today, we're not going to take too much more of your time, okay? Oops, sorry. So for this problem here, you have a linkage system here. It's got 3 rigid bodies, OA, AB, and CD. They're linked at 2 hinges here. So there's a hinge here at A and B here. And they've supplied you with the angular velocity omega AB. So that's 40 radians per second. That's given to you. And what they want you to do is find 2 things. The angular acceleration OA, so the angular acceleration of this rigid body over here, and the acceleration of the point D, which is up here. And all the geometry is given to you for this problem. So always when you have these kinds of rigid body problems, you try to start by finding hints or shortcuts or valuable pieces of information that can help guide you through the problem. For example, in this case here, the first thing you should look for is which rigid bodies are rotating. In this case, you have 2 rotating bodies. You actually have this body here, which is going to rotate along with omega, so that's counterclockwise, so it's going to move counterclockwise here. And there's going to be a counterclockwise rotation OA as well. So that also will determine the velocity directions at points B and A. That's valuable information. You actually know what the directions of the velocities at points B and A are. So if you just look at this here, if I want to draw it, if this is rotating counterclockwise, you know that VB has to be going in the negative direction in X. And the same thing for OA. If it's rotating counterclockwise, you know that the velocity has to be going vertically up like that. So you know the directions of the velocities of 2 points on a rigid body, A, B here. So I'm going to do something that might upset Howard over here. I'm going to use, for this problem, the instantaneous center method and the vector method together. So if you draw the instantaneous center like this, if you draw it for the body AB like this, you can see that the instantaneous center for this problem is actually the point C, which is quite nice because we have all the geometry already. You don't have to do any fancy trigonometry here. You can actually proceed with this. And since we have the angular velocity for this rigid body here, that also translates to the angular velocity for the instantaneous center. So at this instant here, you have that the angular velocity of the instantaneous center is equal to the angular velocity AB, which is 40. Since you have the angular velocity and the geometry and the distance to the points, you can get the velocities A and B immediately. So in this case, VA would be 200 millimeters times the angular velocity, and VB would be 150 millimeters times that. So I've summarized this in this slide. Basically, you have that VB is basically 40 times 0.15, which is 6 meters per second. Sorry, this should be the other way around. It should be like this, sorry. VA is 40 times 0.2 because you're taking it from the point C. So even though OA is 0.1, you're measuring it from here. So 0.2 times 40, that's 8 meters per second, and that's going upwards. Yep. So this instantaneous center here is for the rigid body AB. It's valid for this rigid body. Since we have the angular velocity of the rigid body, then it's the same for any 2 points on the rigid body, including between like C and B or C and A. Okay. And just keep in mind that this is at this instant here, right? Because when this thing starts moving again, it will no longer align at C. So you don't have this expression here for VB and VA is not valid for every time, just for this particular instant here where things lined up very nice for us. Okay. Any other questions about this so far? So always when you start these problems with the rigid bodies, try to find useful pieces of information and kind of store them somewhere, because then you can use them to simplify the later equations that you kind of set up, especially if you're using like the vector approach and you might have lots of unknowns. You want to try to remove as many as you can before you try to solve them. So for this case, we're going to try to set up the relative acceleration equations for different points on the rigid bodies here to kind of complete the problem, right? One thing, please you don't have to compute the cross product every single time for the 2D problems. Please keep a note of these things here. So this is just a simplification for the cross product formulas for omega cross R, alpha cross R, omega cross R. These are known things in 2D. You can find them easily. Don't manually compute the cross product in the exam. You're just more likely to make a mistake somewhere by accident. Okay. So we'll start with the first relative acceleration equation. We're going to pick the point between O and A. We're going to pick the rigid body OA first. So the absolute acceleration at A is equal to the absolute acceleration at O, which is 0 because it's a hinge. It can't be moving. Plus alpha OA cross RA with respect to O. So the angular acceleration OA cross the relative position vector from A with respect to O, plus omega cross R for this. So omega cross, or omega OA is not known in this problem. We have to find this. It's an unknown in this problem here. Well, actually, sorry. I think because it lines up with the instantaneous center, technically we. What did I do? What I miss? Oh, I'm sorry, I missed the detail. So since we have the velocity at A, we have VA, and we have the position vector here, we actually can find omega OA. Sorry, it's not equal to the instantaneous center. We actually find it from VA over 0.1, which is, I kind of missed it. It was here. So omega OA is equal to 8 over 0.1. That's 80 radians per second. We found it because we know the velocity at A, and we know the position vector of A with respect to O in this case. It doesn't line up with omega AB. It's different. These are two different rigid bodies. They have to have different angular velocities. Okay. So this omega OA is what's going to be supplied to this relative acceleration equation here. So this goes in here. So if you're to evaluate the cross product formulas using these formulas up here, you can get this simplification. So using the fact that the position vector RA with respect to O is positive 0.1 in x and 0 in y, your absolute acceleration, the x component should be minus omega squared times 0.1. That's going to be minus 640 meters per second squared. And the y component will be 0.1 times alpha OA, which we don't know yet. So we've simplified something here. So now we figured out one of the components of the acceleration at A, the absolute acceleration, but we still have one unknown here. Any questions about the motion of the rigid body OA? So we'll do the same thing again. So we're going to set up the equation exactly the same way, but for the rigid body BC now. So the acceleration at B is equal to the acceleration at C, also 0 because it's a hinge, it's not moving, plus alpha cross R plus omega cross R. Again, substitute with these formulas up here, don't do the cross product yourselves. The relative position vector of B with respect to C, you just go up by 0.15 meters to get from C towards B. So the absolute acceleration of B with the x component is minus 0.15 alpha BC. Again, alpha BC, we don't know it. This is an unknown. And the y component of the acceleration is minus omega BC squared into 0.15. Now, this was actually coinciding with the rigid body, the instantaneous center. So you can set that omega BC equals omega AB, right? Because it's on the same. If I was to extract, I don't think I extracted the figure here. This whole thing can be treated as one single rigid body. It's like a giant triangle here. So this rotation is the same as this rotation here. So the acceleration of the y component is minus omega BC squared into 0.15, which is minus 240 meters per second squared. Okay, it's not the same as what happened between O and A. So in O and A, it's a different rigid body, but here, because it's linked with the instantaneous center, you can count omega AB equals omega BC. That's why we can do that at this instant. Any questions about the motion of BC? So we've figured out we figured out one of the components of the accelerations here. So now it's like we have two unknowns here. We have alpha OA and alpha BC. So we can still set up one more relative acceleration equation between A and B this time. So again, the same setup. It's like you can see that there's like a repeating formula here. I just set up the equation. I substitute the formulas that we have from the last slide, and I tried to find wherever I can substitute a known value. So here, the absolute acceleration at B is equal to the absolute acceleration at A. So both of these, we have them from the last slide, right? We have like values for some of them, different components of them at least. There's not going to be an angular acceleration AB because the angular velocity here was supplied as a constant. It was a constant 40 radians per second, so the angular acceleration at AB has to be 0 as well. So this term wipes out, and you have an omega cross R term. So if you take in the components that we got for the accelerations A and B from the last slides, and you substitute the value of omega AB that you do know into this equation on both sides, you can get an expression like, so ABX equals AAX minus omega squared into the x component of the relative position vector. Again, the relative position vector, you go from A to B, you have to go minus 0.2. And then positive 0.15. That's why I put it like that, minus 0.2 in the x, positive 0.15 in the y. You plug that in there, you'll see that ABX equals AAX plus 320, ABY equals AAY minus 240. And now we're going to plug in the last, the values we got from the last slide where we had I think we had AX and ABY or something, other way around maybe. If you do that, you end up with minus 0.15 alpha BC equals minus 640 plus 320. So actually, you can evaluate alpha BC directly here in this equation. It's 2,133.33 radians per second squared. And the same thing for the second equation. It's minus 240 equals 0.1 alpha OA minus 240. So the minus 240s cancel out, and your alpha OA is actually 0 in this case. Did I move too fast, or did you guys catch up? Is everybody keeping up with that? So just to recap, I set up the relative acceleration equation for A and B, and I used the expressions that I got in the last slide for the different points at A and B. So I have some components that I know. So by plugging in those expressions into here, I get two equations and two unknowns that I can solve for. Okay. So just again, the alpha BC is 2133.33 radians per second squared. Alpha OA is 0. Any questions? So this is one of the things that we were trying to find. So we finally found the alpha OA. Since we have all the other alphas now, we can actually get the motion at D as well. So we need to do this one more time. We have to set up another relative acceleration equation between C and D. And that's convenient for us because C is not moving, so that's like a nice way to do it. So for this part, again, remember that this is one rigid body here, the whole thing. C, B, D is all one rigid body, so the omega BC transfers to the body CD, and that's equal to the instantaneous center. That's equal to the omega AB. So that's the same angular velocity we're going to use for this. So AD, the absolute acceleration at D, is equal to AC, which is 0 because it's a hinge, plus alpha cross R, plus omega cross R. We have both of these. The alpha BC, we got it in the last slide here, so we're going to use that. The position vector RD with respect to C is positive 0.225 in Y and 0 in X. And if you plug in the expressions, you can immediately evaluate the two components for the acceleration. So ADX is minus 0.225 alpha BC, and that's minus 418 meters per second squared. Then the Y component of the acceleration is minus omega squared into 0.225, and that's minus 360 meters per second squared. And if you want, you can get the magnitude as well. It's 576.89 meters per second squared. So we got the two things we were looking for. So you can see there's like a kind of methodical, approach to how to do this. First of all, you kind of define the relative acceleration vector. Pick 2 points. Define the equation itself. Get the position vector, and then substitute, and see if you can figure out all of the any of the values that you might have compiled when you were starting the problem, looking for shortcuts or known values. Okay. That's the approach that I normally do. In this case, I just kind of use the instantaneous center just so that I can transfer the omega here to the rigid body here, and to get the velocity components. I suspect that you could have probably gotten those even with solving the full system. So in this case, it kind of came in the end to two unknowns and two equations. I think even if you didn't use the IC method, you would have just gotten a bigger system that you could solve anyway. It's not like you needed the IC for this. Just like Howard said, anything you can do with IC, you can also do with the vector approach too. Does anybody have any questions about the problem? All right, so we're done now. We'll stick around if you guys have any other questions though, okay?